Yes, good evening, everyone. Welcome back.
Good evening, sir.
Good evening, sir.
Good evening, sir.
Yes, welcome, everyone. Hope my voice is clearly audible. Yes, anyone confirm?
Yes, sir.
Okay. Yes, you're Priya.
Yes, sir.
So, any doubts from yesterday's class?
Sir.
Yashwant?
No, sir.
Okay, then. Okay, so we'll go ahead. So, a quick revision of what we begin at the fag end of the session. So just introducing the principle of strain, right? Stress and strain, correct?
Yes, sir.
Okay, so yeah, metal body subjected to a tensile force. Okay, having two strains on its body. On one side only I'm talking about, it is happening every side of the metal body. Okay, so, or metal block. How many sides the metal block is having? How many sides the metal block is having? How many sides it is having?
Six, sir.
The top is one side, bottom is another side. Leaving top and bottom, how many sides? How many more sides? This side,
Four, sir.
this side, this side, this side. So total, how many sides? A rectangular or square metal block will have how many sides? 6 sides?
Yes, sir.
Yes, I can represent this EL and ET in any side. Okay, so it is in the surface of the metal block. I'm saying means it is happening within the body itself. Okay, so here also I can mention that. Okay, so in the force axis, EL is acting. 1 minute. EL is always longitudinal strain. That is the axial strain. It is in the same axis of your force acting on the body. Okay. What about ET here? So with respect to this point, okay, so EL is this way, EL is this way. It's also EL. Then what is happening to this? What is this? What is this in the metal block? Okay, I'm calling this as length. I'm calling this as width. What is this actually? Thickness, correct? Yes or no? Left getting?
Yes, sir.
So it is thickness. So that means there is a strain acting on this body to reduce the thickness as well. Okay, that is ET is going to reduce the thickness. Okay, ET is perpendicular to the EL. Okay, so EL is trying to increase the length. So EL contributes for increase in length. So length will increase by L plus delta L, whereas ET contributing for decreasing thickness as well as decreasing width. Agree, everyone? Agree? Yes or no?
Sir.
Yes, sir.
Then tell me what's your area of cross section, cross sectional area of this metal block. Area of cross section. W into T or L into W? L into W is a surface area, top surface area as well as bottom surface area, correct? What is the area of cross section mentioned in the LO?
W entities.
Yes, W into width into thickness. Getting everyone? All of you getting?
Yes, sir.
So this understanding is very important. So EL is increasing the length. So L is going to become L plus new length will become L plus delta L. And new thickness will become T minus delta T. And new width is going to become, okay, so W minus delta W. Okay, like that we can write. Okay, so let me say here the new length because of EL. In this case, it is tensile. EL is tensile. Therefore, L new becomes L plus delta L. Exactly speaking, because of ET, So this is longitudinal tensile strain. Okay, and this is transverse compressive strain. So if longitudinal is tensile, automatically ET will become compressive. Transverse compressive. Because of that, T nu is going to become the whole thickness minus change in thickness. And similarly, your width nu of your metal block is going to become old width minus change in width. Okay, that's how it goes. Okay, but the volume of the metal block remains what? Same. Volume remains constant. Agree, everyone? Okay.
Yes, sir.
Yes. So come back to this. What we are interested in this metal block is it's a metal wire. Okay, so resembling a rectangle piece as shown. Okay, so we are treating this metal wire as a rectangle piece that is having a resistance R. Okay, that is the metal block. Okay, the metal used to form this rectangle piece having a resistivity rho and length of so many centimeters or millimeters and area of cross section A, all as defined. So when there is a chance of change in length, there is a chance of change in resistivity, and there is a chance of what? Change in area. Okay, subjected to the force acting on the metal block. So what will happen to the resistance? That's what we are addressing. So the change in resistance is going to be function of change in length, function of change in area, and function of change in resistivity. And just we are applying the superposition, we are finding the delta L effect on delta R, delta A effect on delta R, and finally delta rho effect on delta R. So contribution due to delta L, contribution due to delta A, and contribution due to delta rho. So giving you the final change in resistance. And mathematically, this is perfectly all right. Agree, everyone?
Yes, sir.
So now let us find, okay, let me take the equation. R is equal to rho L by A. So first tell me what is dou R by dou L. Partial differentiation, because R is function of many independent variables. Rho and L are independent. Rho and A are independent. Okay, there is no connection between them. So they are independent variables. So it's a differentiation only, but we call it as a partial differentiation. Yes, differentiate R with respect to L. What is the resultant? Rho and A will become a constant. Agree?
Yes, sir.
Rho by A will be the resultant. Getting it clear?
Yes, sir.
Then what is dou R by dou A? It's fine. What is dou R by dou A?
Royal. Sorry.
Rho L by minus rho L by A square. Sir.
Yes, you have to feel it like rho L into A power minus 1. Then do the differentiation. Then it is going to be minus 1 into rho into L is out of differentiation. They are constant. So then it is going to become A power minus 2. Agree?
Yes, sir.
Then what is the resultant? It is equivalent to minus rho L by what? A
A
square.
square.
Yes, that's your dou R by dou A. That's fine then. Okay, little challenging. Okay, then dou R by final parameter dou rho. Change in R due to change in resistivity. Okay, you are finding sensitivity. So how sensitive R to L, how sensitive R to A, and how sensitive R to rho. That's what we are doing. Yes, differentiating with respect to rho using numerator. So therefore, the result is going to be simply length by area of cross section of the metal block. Okay, correct. Getting everyone?
Yes, sir.
Then substitute them in the expression of delta R. Then what is delta R? Delta R is equal to, therefore, delta R is going to become dou R by dou L. It is rho by A. N2 as per, I'm just substituting them in this equation. This equation only, dou R by dou L into delta L, dou R by dou A into delta A, dou R by dou rho into delta rho. Substitute. We'll see what is the resultant. Yes. So this is dou R by dou L into delta L. Plus dou R by dou A is minus rho L by A square into delta A. And then, okay, because it is minus. And finally, dou R by dou rho is L by A into delta rho. Agree, everyone? Yes or no?
Yes, sir.
Yes, Prabhanchan, following right.
Yes, sir.
So then we'll go ahead. Yes. So give me the equation now once again. Let me have a copy of the same. So delta R is equal to rho by A into delta L, correct? Yes. Minus second component is, it is rho L by A square into delta A. Second component. Third component is L by A into delta rho. Agree? That's what we are getting, right?
Yes.
So then let me divide by L, multiply by L. Divide by A. In order to divide by A, I'll take this as A and A. Agree? Is it okay? Because I have A square, I'll split that into two terms. And here let me multiply by rho and divide by rho. Okay? Easy, everyone? All of you getting?
Yes, sir.
Then you know very well what is rho L by A. Interesting logic. What is rho L by A?
R.
Our very old resistance, correct?
Yes.
Yes or no? So that's a resistance before application of your strain on this metal body. Okay, right? So R is simply rho L by A. So replace rho L by A by R, then take it to the left side. Then it is going to become delta R by R. So delta R by R is equal to the simplest equation to remember, delta L by L minus delta A by A plus what? Delta rho by rho. All of you getting? This is a much better equation to remember, right? Yes or no?
Yes.
This is what happens. Okay, to the change in resistance. It's a unitless parameter because it's delta R by R, it's unitless. So unit change in resistance, we call it as, it's a unitless change, but anyway, it's a unit change in resistance. What is the change in resistance with respect to the original resistance? Okay, that is a function of change in length with respect to the original length minus change in area divided by original area plus change in rho divided by original rho. Okay, hope it is clear.
Yes, sir.
Now, what is delta L by L? What is delta L by L? Delta L by L is nothing but your EL. What is that? Longitudinal strain acting on the body. All of you getting? Yes or no?
Yes, sir.
So usually delta L is going to be in very, very small. So this is going to be, so EL going to take the expression. It is change in unit change in length. Okay, with respect to the change in length with respect to the original length. And usually the length assuming meter and the delta L is going to be in the order of micrometer. Therefore, this is usually micrometer per meter. That's how we get the strain definition. So usually we call EL any strain, we call it as a micro strain. We call it as a micro strain. It's unitless parameter. Either you say micrometer per meter or simply you can call it as a micro strain. Okay, because it's unitless. The strain is in micro, you call it as a micro strain. Getting? So EL usually in metal blocks, assuming there is a little elasticity. So when you stretch it, it is going to get stretched only by little factor, so that delta L is not visible. It is going to be only in the order of micrometers, which we can't see with our eyes. Correct? Yes or no? All of you getting? Yes or no?
Yes, sir.
So we'll see what is this magnitude little later. So by default, your strain is going to be only in the order of micro. Okay, even if you get a milli strain, that's even a huge number. Usually in the metal block, the strain will be in the order of few hundred micro strains only. Few hundred micro strains only. Strain in terms of strain. Okay, it's to make sense. Microwatt. If it is a capacitor, you say microfarad. If it is a inductor, you say millihenry, right? So for strain, what is a unit? Strain only. Okay, because it's a unitless parameter, because it change in length divided by original length. Hope it is clear. Hope it is clear.
Yes, sir.
So then get back to this metal body. Let me have a copy of this. Otherwise, let me draw it once again. So this is the one subjected to the force. Okay, in fact, I should take it from here. Take this way. It's looking better, right? So this is a point. Yes, this is where the force is acting. Is he right? Okay, both are pulling force, pulling the body on the two sides. Then in the top surface, what we have is our strain. So with respect to this top surface, I have marked this as the EL. Okay, this is also EL, and this is our component ET, and this is our component what? ET. Agree, everyone? Already mentioned EL responsible to increase the length, ET responsible to decrease what? The thickness of the metal block. So this is your thickness, and this is your width. Let me take this as the width. Is he right? Is he right? Clear? Once again. It's everywhere. Even you can mark it here. Okay. So EL is responsible to increase the length. So the length increased by delta L. Who's contributor? EL is a contributor. Okay, right? So therefore, with respect to this side, it's a length. So that becomes L plus delta L. What does EL means? We are saying EL is equal to it's delta L by L is nothing but EL acting on this body. Okay, in the length. It is the one responsible to increase the length. So change in length by original length is itself your longitudinal strain. Getting your Priya?
Yes, sir.
Then what about ET? In the same metal block, what is the ET then? What is transferred strain? EL is positive because it is increasing the delta L is positive or negative?
Positive, sir.
Length is increasing or decreasing?
Increasing, sir.
1 minute. Let me increase the volume little. Okay. So length is increasing. So EL is positive because tensile always makes positive strain, whereas ET is compressive. That is decreasing your what? Thickness as well as width. So similar to the one, EL is a contributor for the length. So therefore I call this delta L by L as EL means. Can I say similarly ET is nothing but delta T by T as well as delta W by W. Agree? All of you? Yes or no?
Yes, sir.
Getting everyone?
Yes, sir.
Okay, that's your, but it is a negative one because it is compressive. Since it is negative, delta T is negative. Why it is negative? Delta T is negative, delta W also negative. So it is going to be a negative one. Compressive always a negative strain. I'm just introducing what is meant by positive strain, what is meant by negative strain. Okay, so tensile is known as shortly a positive strain because that is the one going to increase the length, whereas this transverse is, in this case, it is compressive because EL is tensile, automatically it should be compressive. Therefore, it is a negative strain, and whatever the parameters defining ET are negative. So T is getting decreased, W is also getting, width is also getting decreased. So delta T is negative, delta W also negative. So the total thickness decreases, the total width decreases. Okay, right? See this. So this is decreasing the width. So the final resultant width is going to become what? W minus delta W, and the final thickness is going to become what? T minus delta T after application of the force. Is he? Everyone? Getting?
Yes.
So now the point is why we are talking about this means we should know what is a contributor here. We are going to connect change in resistance with respect to the strain. We're going to connect the change in resistance with respect to the strain. So we wanted to connect EL and EL. I'm going to take hereafter, it is shortly E. E hereafter represents only your longitudinal strain. Okay. So then I can say delta R by R is equal to shortly, or delta L by L, that is shortly I'm calling it as E. Okay, ELR, E. E is my strain. By default, it's axial strain or the force axis strain. Remember that. So I'm going to replace delta L by E. That's my strain acting on the body. By default, the moment I say strain, it's a force axis strain. I'm talking about the longitudinal strain only. So then if I say it is a strain, transverse strain, I should call it as transverse strain. By default, strain means talking about force axis strain. So I have to give a stress on the opposite strain, which is acting on the body, that is the transverse strain. So simple saying of strain doesn't mean that it's a transverse. It is by default meaning only the axial strain. Getting? All of you getting this point? Yes.
Yes, sir.
Okay. Now, can anyone tell me, do we have any connection between, so delta R by R, this is equal to E. So minus I have delta A by A plus delta rho by rho. That's all. Okay. The goal is I want to connect delta R by R as a function of strain only. I want to make delta R by R only function of the longitudinal strain or axial strain. That's a plan. So the first term alone changed, but rest of the terms I need to change. Okay. So for that, I'm looking for a connection between ET and EL. So tell me, what is ET as a function of longitudinal strain? Anyone? What is ET as a function of longitudinal strain? Anyone? Assume the metal block as a Poisson's ratio of mu. What is the symbol? Poisson's ratio of mu. Okay, so like this. It's not gamma, take it as mu. Okay, another, how you call the symbol?
Mu, I guess.
Correct. It's like this mu only. This is also called as mu. This also we can call it as mu, but that's a different symbol. This is a micro, and this is representing mu, that is representing another parameter called Poisson's ratio of the metal block. Poisson's ratio of the metal block. Okay, yes, it is given. So Poisson's ratio of the metal box is given means, then I'm giving you an hint. So what connection exists between ET and EL? Yes. And can you tell me, in the metal body experience both EL as well as ET, whether they are equal in magnitude? When I apply the force on this metal body, whether the EL and ET are equal in magnitude? Both are strain only, right? Yes or no?
Yes.
Are they equal in magnitude or different?
Equal, sir.
Because they are opposite forces. They are opposite strains. One is acting on the force axis, another one acting opposite to the force axis. So they are opposite. One is tensile, another one becomes automatically compressive. Suppose if I apply compressive longitudinal, then transverse will become automatically tensile. Able to follow me? Are you getting me point? Are you getting me point? Yes or no?
Yes.
If I make a compressive force, that is going to be on the, that is your force axis, then EL will become compressive, that is going to reduce the length. The one who is going to decide your length, increasing length or decreasing length, that is your longitudinal strain. So it is still delta L by L, but delta L is not positive, it is negative. So compressive strain is going to, there is a longitudinal becomes compressive, which is going to reduce the length, whereas ET will become automatically, it's a transverse, that is going to increase the thickness, also going to increase the width, that is going to become a positive strain, that is going to become tensile. So when you apply a compressive force, it is going to result in a compressive longitudinal strain and tensile transverse strain. Hope you are able to understand these points, all of you. Yes or no?
Yes, sir.
Okay, we'll show that environment, okay, soon. If I reverse the force acting on the body, what will happen? We'll see that. Okay. Yes, that's another situation we should know. Yes, now I'm asking you the simple question whether the two strains are equal or different. Whether they are equal or different. Yes, magnitude of ET not equal to magnitude of EL. That's the first fact. Then what does ET means? By default, ET is given as minus the Poisson's ratio times your EL. That's a connection between ET and EL. That means the Poisson's ratio of the metal block only, or the metal used to form this rectangle block only, or box only, decides your connection between ET and EL. So when you go for the metals, any metal you take, the mu is less than 1 only. The mu will be something like 0.4. The Poisson's ratio something around 0.4 or 0.6. What will happen? What will happen? Your transferred strain is going to become, if it is 0.4, it is going to be only 40% of longitudinal strain only. Getting? Yes or no? All of you getting?
Yes, sir.
Yes, that's an important point to consider. So ET is nothing but minus mu times your EL. So this is your EL and this is your ET. Now let us play. So the sign is also okay given. EL is positive strain. That is tensile strain. What happens to ET? Play with that. EL is positive means automatically ET will become negative as per the expression. So it is going to become compressive strain. Yes, negative strain is nothing but compressive strain. So it's a negative strain, negative, and this is positive strain. So let me take it as a tensile strain. That is a positive strain, and this is going to become a compressive. That's a negative strain because the expression itself is saying everything. Okay, ET is okay minus mu times your EL. Okay, but the magnitude of ET will be less than modulus of ET will be less than, because ET is negative. So modulus of ET will be less than always EL. Okay, that's a fact. If it is, for example, 0.4, so EL is around 100 micrometer per meter, ET will be, assuming Poisson's ratio is 0.4, only 40 micrometer per meter will happen in the transferred state. Hope you're getting? Hope you're getting? Everyone?
Yes, sir.
Suppose if EL becomes compressive, that is a negative strain. If EL is a compressive strain, it's a negative. EL itself is negative means what is going to happen for ET? Remember this equation, that's very easy. Yes, that's a fact, mechanical fact. Yes, what happens? EL is negative means negative will become positive. Therefore, this is going to become tensile or positive strain. Okay, so any strain tensile, it's increasing. Any strain compressive, that is decreasing. So increasing one, we call it as positive strain. The one which is decreasing, we call it as what? Negative strain. Hope it is clear. Hope it is clear.
Yes, sir.
Okay, so the important equation is this through Poisson's ratio of the metal block. That's very important. Okay, connection is given. Okay, between ET and EL. 1 minute. Now, in the metal block, we call delta L by L as what? EL. Then tell me what is delta A by A? What should I call this? This can be later taken as shortly E. What is delta A by A?
Mu times EL, sir.
Yes. Mu times EL, Poisson's ratio times EL.
Yes, sir.
Delta A by A, I'm asking.
Okay, sir.
Okay, what is your area of cross section? Width into thickness, correct? Yes or no?
Yes, sir.
I am looking for change in area. So then there is a change in width, plus or minus you take. There is a change in thickness, plus or minus this you can take. Then tell me what is the change in area? You have to play like how you played for the change in resistance. How we played for change in resistance? It is nothing but dou A by dou W into delta W. Getting everyone? Getting Akshaya?
Yes, sir.
What is the condition here? There is no change in thickness. Then what is the next component? Dou A by dou T into what? Delta T. Where? What is not changing? Delta W is not changing. That's your superposition. Yes, now tell me what is delta A. Therefore, delta A is equal to what is dou A by dou W? T itself, correct? Into delta W. Getting you, Priya?
Yes, sir.
Second component, dou A by dou T is simply W itself, width itself, into what? Delta T. Easy. That's easy, right? Yes or no?
Yes, sir.
Then multiply by W, divide by W. Then multiply by T, divide by T. Then what is W into T?
Area, sir.
Yes, what is W into T? Width into
Area,
thickness.
area, sir.
Area itself. Then what do you get then? Take it to the denominator. Delta A by A is known now. What is that? Getting Yashwant?
Yes, sir.
It's pure mechanical thing. Okay. So delta T by T. Yes, already we have made delta W by W is because of whom? ET. Delta T by T is also because of whom? Getting the point? Yes or no?
Yes, sir.
So therefore it has to be replaced by what? Shall I call this is equal to 2 times ET. Agree? Yes or no?
Yes, sir.
Sir.
Because delta W by W is what strain? Transverse strain. Who contributed for change in width? ET. What contributed for change in thickness? ET. So this is ET. This is ET. So it is twice that of ET. That's what delta A by A is. Clear? Everyone? Yes, that's an important point. Yes, without this we can't proceed. So this is 2 times your transverse strain. That's your delta A by A. So delta L by L is your EL and delta A by A is 2 times your transverse strain. Then see the expression. So this gives more meaning now. So you got delta L by L, you got delta A by A, and you got delta rho by rho. So again get your expression for change in resistance. Okay. Yes, what are the change in resistance now? The change in resistance to original resistance. Once again, writing the equation delta L by L minus delta A by A plus delta rho by rho. Agree, all of you? Then I'm writing delta R by R is equal to, this is nothing but EL minus of delta A by A. We know that that is 2 times ET plus delta rho by rho. Agree, all of you? Yes.
Yes, sir.
Then we know delta R by R is equal to EL minus, we know since ET is equal to minus mu times EL. Yes, take it to the expression, it is going to become plus. Agree? What is that? 2 times the Poisson's ratio times your EL plus delta rho by rho. Happy?
Yes.
Yes, now take EL common. Then delta R by R is equal to take EL common. What is the remaining? 1 plus 2 times the Poisson's ratio plus 1 by EL into delta rho by rho. Agree? All of you getting?
Yes, sir.
Okay. And finally, I'm going to make the expression delta R by R is equal to, this is my strain, longitudinal strain. Shortly, I'm going to denote it by E, and entire factor, I'm going to call it as gauge factor. Sensitivity factor, I'm going to call it as gauge factor. All of you getting the point? All of you getting the point?
Yes, sir.
That's a strain gauge factor. I'm shortly calling it as a gauge factor of the strain gauge. So that is known as simply either G dot F, or it will be given as E into S suffix G. Okay, sensitivity of the strain gauge factor. So therefore hereafter I can remember delta R by R, okay, divided by the applied strain is equal to the gauge factor Sg, which is nothing but 1 plus 2 times Poisson's ratio plus 1 by your strain into delta rho by rho. Agree? All of you getting this point? Yes or no? Okay.
Yes, sir.
So this is talking about connection between unit change in resistance. What is E? E is nothing but it's delta R by R divided by delta L by L. So that is giving you the change in unit change in resistance divided by unit change in length is nothing but your gauge factor. Is nothing but your gauge factor. Easy of the strain gauge. All of you getting? Yes or no?
So gauge factor is gauge sensitivity, sir.
Yes, of course.
Okay.
Who is responsible to convert strain into change in resistance? Finally, the gauge factor only. Correct?
Yes, sir.
So I'm just giving you the proof, but what will be given to you is straight away SG will be given to you. You have to play with this equation only hereafter. So you'll be given, okay, straight away gauge factor. Suppose if given the Poisson's ratio, then you should be knowing that what influences your gauge factor. This is 2 times your Poisson's ratio, and this effect is what we call as very technically in metals this effect. Okay, so 1 by strain into change in unit change in resistivity. That's what we call as piezo resistive effect. We call it as piezo resistive effect. Okay, right? In metals. So this alone what we call as piezoresistive effect. So 1 plus 2 times Poisson's ratio plus piezoresistive effect makes your gauge factor as G or G dot F. Hope it is clear, Akshaya.
Yes, sir.
Getting Prabhanjan? Okay. Yashwant?
So getting, sir.
Okay, yes. So hereafter the point is, so in strain gauges, a metal block or a metal wire, okay, of length L, area of cross section A, and resistivity rho. Okay, so there is a one. We'll see how we are going to form the strain gauge. That's a strain sensor. Okay, what we are going to remember, what we need to remember is only the gauge factor SG is equal to change in resistance, unit change in resistance divided by unit change in length. Okay, that is what we shortly memorize as delta R by R divided by your longitudinal strain, shortly the strain in the body. Okay, easy everyone? Ready?
Yes, sir.
Okay, so here R is nothing but zero strain resistance of the strain gauge. It is called as zero strain resistance or unstrained resistance of the strain gauge. Zero strain resistance of the gauge. I'll show you the representation of the gauge, how it can sense the strain. We'll see. Okay, zero strain resistance. Delta R is the change in resistance due to strain. Change in resistance due to applied strain. Due to applied strain in the metal block where we are going to paste our strain gauge. I will show that ambience. Okay, due to applied strain. Okay, so E is nothing but simply the strain. Okay, in the metal block where the gauge is pasted. Hope it is clear, everyone. Hope it is clear. So from this, can you tell me what is delta R? So we know delta R by R from here is nothing but gauge factor into the strain in the metal block. So therefore, change in resistance is going to be R into strain gauge factor into E. And straight away, this is your sensitivity of the strain gauge. So this is the one responsible to convert the applied strain into change in resistance. Is it linear or non-linear?
Yes.
So what strain gauges are doing, sensing the strain, converting that into change in resistance. Simple. Yes or no?
Yes, sir.
Okay, a strain gauge is a sensor sensing the strain E and then simply convert that into change in resistance through the factor gauge factor SG or G dot F as the gauge factor. Sometimes they will mention G dot F, sometimes they will mention SG. Okay, fine. Getting?
Yes, sir.
So now let me show the strain environment. Okay. I have to give one more mechanical connection. Refer this body again. Okay, yes, the force is acting on the given area. So this is exactly the area it is acting on, correct? Where area is still what? Area is still what? Width into thickness. Now tell me what is the stress on this metal, because I thought of introducing that itself first. Okay, so I have mentioned it, but okay, so I didn't talk about it in detail. Okay, we'll talk about that. Okay, so stress is nothing but force per area. Okay, correct. So referring this box, it's easy understanding of stress. So here itself, let me write stress is nothing but stress in the metal block is nothing but force acting on the given area of cross section. Force is going to be in newtons and this is going to be in meter square. So the force per area is going to be Newton per meter square. There exists connection between stress and strain. So we'll see how it goes. I am applying a force to the metal block. Due to the application of force, what we are getting is stress only we are getting. Yes or no? This stress only converted into strain. This strain only converted into change in resistance. This is clearly known. Who is doing the conversion? Strain to delta R. Who is doing the conversion? Strain to change in resistance. The gauge factor is doing that. Correct? Clear? So this is clearly well known. Then who is converting stress into strain? Who is converting force into stress? Area is doing that job. Correct? Because stress is nothing but force applied divided by area of cross section. So we know this connection. This connection is well known. This connection is known. And who will bridge these two connections? Stress and strain connected by the most important parameter. That's our modulus of elasticity. Young's modulus of elasticity. So then what is stress by strain? Yes, you should know stress by strain is nothing but Young's modulus. Agree, all of you? Yes or no?
Yes, sir.
Yes, sir.
So E is nothing but, so this is your E. So what is E? E is nothing but, what is stress? Force per area divided by what is strain? Either you call delta L by all L or simply call it as what? Small e. So therefore it is F divided by small e into area. That's all. Okay, that's your Young's modulus. So what this is going to serve, from this Young's modulus, you can find strain. That's ultimate goal now. So tell me what is strain? Therefore, from this, what is strain? Therefore, the strain is equal to due to stress or due to force. Straight away. Yes, connected. What is your strain? Strain is equal to force divided by Young's modulus into area. That is your strain. So this is how straight away one can convert applied force into strain. Yes or no? Yes. Yes or
Yes,
no?
sir.
So then the overall input is going to be your force and overall output is going to be what? Your change in resistance. Therefore, it can comfortably act as a force sensor as well. Whenever you want to measure the force, you can happily use a strain gauge. But provided the strain gauge is not going to create the strain gauge is the sensor which is pasted on the environment or surface where there is a strain. We're going to paste the strain gauge on the surface area where there is a strain. Then through the gauge factor, it will convert the strain into what? Change in resistance. Then who will convert stress into strain? There is going to be a primary sensing element. That primary sensing element is responsible to convert the force into stress. And that is responsible to convert stress into strain. So we are going to have a primary sensor. That is what we call technically as load cell. We call it as technically load cell. Getting everyone? Yes or no? Yes.
Yes,
Sir,
sir.
So load cell is the primary sensor sensing the force and producing strain. And here what is coming into play is our strain gauge. So strain gauge is always not the primary sensing element. It is a secondary sensing element. It is not going to create the strain. Somewhere there is a strain means you can use strain gauge to sense that strain. That's all. Okay. So strain gauge is a strain sensor. It is not creating any strain. Okay, so this is your strain sensor. That's all. Strain gauge is a strain sensor, and who is producing strain for us means always the load cell. So load cell will act as the primary sensing element. There are two sensing elements. So this is primary sensing and this is secondary sensing. Hope it is clear, everyone. Yes
Sir?
or no? Yes.
So load cell actually senses force and it produces stress.
Yes, of course. And then the moment there is a stress in the metal block, automatically there is a strain as well.
Okay, sir.
Understood?
Yes, sir. Yes.
Because stress and strain are there in the metal block. What you perceive, either you perceive stress or you perceive what? Strain. Correct?
So
So
the
what I
output
want
of the
to
load cell.
what I want to prove is force is converted into stress. When force is acting on the given area of cross section, it is converted into stress. Because of that stress, through Young's modulus, we are getting the strain. Getting?
Sir, yes, sir.
Then if you present a strain gauge, if you place the strain gauge on the surface of the metal block, which is experiencing the strain gauge will sense such a strain and then will produce change in resistance. Then we can comfortably play with this equation. Getting?
Yes, sir. Understood.
Hope the point is clear, everyone.
Yes, sir.
This is purely mechanical thing. Yes, biomedical students, anywhere you studied this? In biomechanics, somewhere?
Sir, in sensors and instrumentation itself.
You studied anyway. Okay.
Yes.
Okay, then that's good. Okay, so you are familiar to the stamps. Okay. Yes, Akshaya.
Yes, sir.
Okay, then that's fine then. Okay. Yes, it's as a instrumentation engineer. Okay, both biomedical as well as instrumentation students. Only the applications are different. Okay, you are in the biomedical field and they are working in the plant. Okay, application is different. Okay, but the basics, okay, they are covering, and what you are covering is almost same only. Okay. Yes.
Yes, sir.
So now let me talk about first what is called a load cell. Load cell means it's a cell going to sense a load. Load is nothing but force. Load is nothing but force in so many kilonewtons. Force is going to be so many kilonewtons. Any example? Can you say load cell somewhere where the load cell is used? Yes. Yes or no? Even if you measure weight of even tons, yes, we have weighing machines. Even a small weighing personal scale, normal electronic personal scale to supermarket weighing machines to even the one which is going to sense the load of what? Load of carriers, goods carriers. Yes or no?
Yes, sir.
Yes, that is going to be in so many tons, 1 ton, 2 ton, so much weight. What is 1 ton weight?
1,000 kilograms.
Yes, 1000 kilograms is 1 ton. Okay. Yes or no? Almost. Okay, so average of almost around 15 to 16% is nothing but our 1000 kg. Correct? Yes, we need machines to sense that weight. Okay, we have machines built. Okay, yes, that is what exactly the load cell is. The cell, it is a mechanical block only. We are calling it as a cell. That is getting loaded and that is getting stressed and that is going to produce a strain. That's where we are going to use the secondary sensing elements. We call them as strain gauges. All of you getting this point? Yes.
Yes, sir.
So any weighing scale or any weighing machine definitely will have the load cell, will use the strain gauge. Okay, then a lot of transduction and signal conditioning is happening inside weighing machines. Okay, the output may be a digital readout. Now we see only digital readout in weighing machines. Okay, no analog readout. Getting Ashwant?
Yes, sir.
Yes, that's a good example of a load cell. Okay, we are familiar, we are seeing them, but we are not connecting. Okay, that's a fundamental. Okay, that's what we call as a load cell. That's a primary sensing element. We are talking about that only. Okay, right? So first let me introduce a load cell. So let me take a vertical block, something like this. need to change orientation of the tab little. Okay. Okay, that's my metal block. Okay, that's what we call as a load cell now. Okay, this metal block, I'm giving the name as load cell. So this is rigid, it is not free to move. Okay, so it is rigidly pasted on the surface where it is placed. Okay, it cannot move. And then I'm going to apply a force in the order of kilonewtons. I'm going to apply the force only one side. I'm going to apply the force. So force in so many kilonewtons. Okay, it may range from 0 to some kilonewtons. Okay, say for example, I'm going to apply 100 kilonewtons of force. Okay, on this load cell. Okay, so yes, what's a geometry? Spec, what is this? Let me call this as what do you call this? Length or height? Let me take it as a height. So this is height. Okay, then. And this one. I can take it as a
Length.
length. And I can take this as what? Width. Or I can buy previous thing. This can be called as what? Thickness also. Nothing wrong. Correct? Either you call it as height of the cell or thickness of the cell. Which one you want to play with? Height or thickness?
Thickness itself.
Both are same, right? Correct?
Yes, sir.
Okay, yes, let me take it as a thickness or nothing wrong. It may be mentioned as the height also. Okay, sometimes. So anyway, so the volume is going to be height into cross-sectional area. Now the cross-sectional area will become what? L into W, correct? Okay, L into W. Anyway, volume is nothing but height into width into length. That's all. Or length into width into height. Okay. So that's a load cell. So force is acting now. Okay. So L is well defined. W is well defined. Okay. So let me draw the L here so that it won't disturb the strains, which I'm going to mention there. This is my L and this is my width. Hope it is clear. Your Priya, following right?
Yes, sir.
Now tell me, where is your longitudinal strain? On any surface. Again, how many faces available? How many surfaces available? The bottom is not available. Rest is available. Okay. So we have 1, 2, this side is 3, this is 4, we have 5. So in the 5 surfaces, we can mention the longitudinal strain and what? Transverse strain. Yes. Immediately there is a stress in this metal block. What is the stress? It is going to be force per area. Okay. Area is given. What is area? Area here is going to be length into width. Following right? Yes.
Yes, sir.
Yes, that's where the force is acting. Length into width is the area of cross section. So then that's where the force is acting. So it is giving you the stress. So force by area, so many Newton per meter square is the stress acting on this load cell. Acting on this load cell. Then tell me, what is your axial strain? So this force is a compressive force that is going to decrease your height. Yes or no?
Yes, sir.
Then what will happen to the length? Height decreases. Volume is equal to length into what? Width into what? Height. So height is decreasing. What should happen for the width and length?
Both should increase, sir.
Both will increase or one will increase, one will decrease. Can you say? We can't say now, correct? All of you getting easily? Getting? Akshaya following, right?
Yes, sir.
So what will be your strain means? The force axis strain is nothing but your axial strain. That's your longitudinal strain. In fact, that is going to be compressive now. EL is compressive. Okay, that is compressing the block. Okay, so it's a compressive strain. Force axis strain is your EL. EL is compressive. So what will happen to ET then? It is going to be opposite. So now you can understand what is going to happen to the length. So ET is going to increase the length. So length is going to become L plus delta L. Getting you, Priya?
Yes, sir.
So it is going to act here. That's how you need to feel. It is going to increase the length. So then similarly play here. Okay, if you play here, so with respect to the width side, so this is the force acting. So it is compressing. So here how you will play. Here how you will play. So this is your EL. Okay, for this surface, this is EL. This is EL, correct? And this will become what? ET. Agree? Yes or no? Yes or no?
Yes, sir.
Then ET is going to increase what? Width. This is width. This is width. This is also width. Agree, everyone? So ET is going to stretch the two sides, means the width is going to increase. Yes, length is increasing. Width is increasing because area of cross section. It's simple. What is your volume? Volume is nothing but what? Area into the thickness. So when thickness is decreasing, area should increase. Easy? Because to maintain the volume constant. All of you getting?
Yes, sir.
Easy, everyone?
Yes, sir.
So now the load cell is going to have is converting force into stress, stress into what? Strain. And this is through area and this is through Young's modulus of elasticity. So what is the strain in this metal block means? Now let me give the dimensions. For this, assume the length is equal to, for example, 4 centimeters, and width is equal to, for example, 2 centimeters. Height is equal to, for example, 5 centimeters. That's the geometry of the load cell. Now tell me the force is given. If I apply full force, maximum force I'm applying, what is the maximum force given? What is the maximum force given? 100
kilonewtons.
kilonewtons. Assuming if I apply maximum force of 100 kilonewtons, tell me what is the maximum stress it is going to develop. Okay, so maximum stress in this load cell is going to be this. What is that? Force per area. So it is nothing but what is the maximum force? What is the area first? Area is length into width. What is that? 4 into 2, that is going to be 8. Yes,
Centimeter
what?
square.
Centimeter square. 8 centimeter square means
10 power minus 4.
minus 4 meter square. Agree? Yes.
Yes, sir.
Yes, sir.
Basic geometry only. Okay, so maximum stress acting on this load cell is 100 kilonewtons divided by what? Area, that is 8 into 10 power minus 4 meters square is the stress acting, maximum stress. Yes, what is that? It's 100 into 10 power 3 Newton divided by 8 into 10 power minus 4 meters square. Okay, so that you can have a feel what is happening in this load cell, how the force applied converted into stress first. So what is the net? 100 by 8 is 12.5.
Yes, sir.
So 12.5 into 10 to the power of 7 Newton per meter square. Such a huge stress experienced by this load cell. Correct? Getting your Priya following, right?
Yes, sir.
Now tell me what is your strain in the metal block? That is your load cell. What strain? What is your EL? So longitudinal strain. I'll also get the budget of ET, get the estimate of ET as well. What is EL? EL is nothing but longitudinal strain is nothing but force per area, that's your stress, divided by Young's modulus of elasticity. Okay, so for that we need this data. So assume this load cell, this metal block as Young's modulus of elasticity as 2 into 10 power 12 Newton per meter square. That's Young's modulus of elasticity. I'm just giving, okay, I'm not remembering exactly what is the Young's modulus of elasticity. Roughly, I'm taking 10 power 12 Newton per meter square as Young's modulus of elasticity. Then what is your E is known, force per area, maximum is known. I'm going for EL max. Maximum longitudinal strain acting on the surfaces. Okay, so it is happening in this surface. It is happening in this surface. In all the surfaces, it is happening. What is that? Maximum longitudinal strain in the load cell. Okay, yes, what is that? You got already your maximum stress. That is 12.5 into 10 power 7. So this is 12.5 into 10 power 7 Newton per meter square. And Newton per meter square, this Newton per meter square also will get cancelled. It's 2 into 10 power 12 Newton per meter square. Then these two will get cancelled. Getting everyone? Yes.
Yes, sir.
And your strain is, of course, unitless. Strain is, of course, unitless because it is delta L by L only. Correct? Yes or no? But in this
Yes,
case,
sir.
it is not delta L by L. In this case, it is what? In this case, it is what? Delta H by H. Because EL is in with geometry. EL is going to change only what? What is EL in this case? EL is nothing but delta H by H only. Understand?
Yes, sir.
Okay, because EL is the one going to change only your H. ET is the one going to change what? ET is the one going to change W, and ET is the one going to change what? Length. Okay, EL is the one going to change your H. Therefore, don't say EL is by habit delta L by L. Okay, getting Akshaya? Following right?
Yes, sir.
Yes, that's your unitless strain in the load cell. What is the number? That's a maximum strain your load cell can offer for this maximum loading condition. Maximum loading, this loading is different. This is completely mechanical loading. This is not electrical loading. Electrical loading is drawing some current from the source. And this is a mechanical loading. Purely you are applying a load on a metal block. Getting Ashwant?
Yes, sir.
Yes. Now tell me what is the number?
62.5
12.5 by
microstrains.
yes, 6.5
into 10 power minus 6. I saw 10 power minus 5.
6.25, 12.5 by 2, 6.25 into 10 power minus 5. Unitless, right? You can say it is meter per meter anyway. So there is nothing but delta H by H. It is meter per meter. That means if the height is 1 meter, delta H is so many meter. Are you getting? If height is 1 meter and delta H will be so many meters. Is it a visible change in height? No, right?
No, sir.
Okay. So you have to see only with the microscope, correct? Yes.
Yes.
Okay, yes. Then EL max is this much. So even a maximum strain, he has put it in micro. So it is going to be 62.5. We call it as micro strain. Okay, it's micro only, unitless, but still we call it as a micro strain. See this? So even for 100 kilonewton load in this geometry, okay, can give you only this much. Okay, so height is already given, but it is never used. Okay, but if somebody is asking what is your change in thickness or change in height, you can calculate because this is nothing but
Del H by H.
yes, delta H by H only, correct? So H is known. You can find out your delta H. See, H is not even meters. How much? Only 5 centimeter. If you multiply by 5 centimeter, it is going to become 5 into 10 power minus 2 again, correct? Yes or no? Yes, what is change in H? Your height is going to change. Height of the load cell is going to change only by this much. It is H into what? EL max, even for this maximum loading. If somebody is asking, just know that how to calculate it. So it is 5 centimeters. So 5 into 10 power minus 2 meter into this EL max, that is 62 micro, 62.5 into 10 power minus 6. Okay, so many, it is unitless. Okay, therefore it is going to be in so many meters. That's what delta H. How much? Delta H is going to become only a small number. How much you get? Also in micro, put it in micro. 62.5 into 5. Okay, so the
3.125 micros, sir.
3.125 micrometers is your change in height of the load cell. Getting Ashwant?
Yes, sir.
Just I have taken a load cell and showing you how you can comfortably play with the applied force, how you are converting the force into the maximum applied force into maximum strain, maximum stress, and maximum stress into maximum strain. You're just seeing what connection you establish from force to stress, stress to strain, and then what influences or what the longitudinal strain influences means it's only influencing the change in height or thickness of the metal block. So what will be the change in thickness of the metal block or height of the metal block? That's what we are saying finally. Understood? So on the way through this example, you are able to understand how force is converted to stress, stress is converted to strain, strain is converted to what? The change in height or thickness. Agree? Yes or no?
Yes, sir.
Okay. So application of force resulting in stress that results in strain. Due to that, there is a change in thickness happens for the load cell. Okay. So we have to paste our strain gauge on the surface in such a way that either it has to sense longitudinal strain or it has to sense what? Transverse strain. So your strain gauge, we are going to paste on the surface of the load cell, can be made or pasted in such a way that it can sense EL or it can sense ET. Accordingly, your strain gauge is going to be longitudinal gauge or transverse gauge, or sometimes we call it as a Poisson's gauge. The one which is going to sense a strain with the Poisson's factor, we call it as a Poisson's gauge. The one which is sensing ET, we call it as a Poisson's gauge. Another one is a normal strain gauge. Getting everyone? Yes or no?
Yes.
Okay, so then I will show the ambience. It's the same load cell. Any doubts till now? Any doubts till now? Yes, Akshaya, you Priya following.
Yes, sir.
Yes, sir.
So this is our load cell. Experiencing the force. This is a rigid surface. The metal block cannot move. The force is applied here. So for the applied force, there is a stress, there is a strain. So how we get the strain? So the strain is EL is this way, EL is this way. Okay. And here also EL is this way, EL is this way. Assuming I'm going to paste a strain gauge here, it is nothing but wire. I'm going to have 1 minute. Let me use a different color. So I'm going to have metal wire bound like this, which is rigidly pasted on the surface. I'm going to paste it a metal wire on the surface. Okay, so don't take it as a strain gauge. It is what a strain gauge is. Gauge 1. Okay, first gauge I am saying. Okay, strain gauge 1. It's not the gauge factor. Gauge factor I use a symbol SG. S dot G, call it as a gauge factor. Sorry, the strain gauge. Left getting?
Yes, sir.
So I play, it's a strain gauge is nothing but it's a metal wire. I pasted like this, a metal wire pasted on the surface. Tell me what is going to happen on this wires. What is going to happen? Because the surface of this load cell is experiencing strain. So here EL is acting, here EL is acting, here EL is acting, here EL is acting, here EL is acting. Agree everyone? Yes or no?
Yes, sir.
So then consider this as the small length of the wire. What will happen if this is stretching? This is not stretching, compressing. 1 minute. 1 minute, stay online. Yes, let me go ahead. Okay. So it is compressing the length. So this is the length. This is also length. This is also the length. This is also the length. So what is happening? So if I take this way, I'm showing only a few turns. Okay. So assuming the strain gauge is like this. Like this. Okay. That's my strain gauge of certain length, overall length, some L total we can say. So at the edges, what's happening? Because it is pasted on this surface. So here EL is acting. Here EL is acting. Here EL is acting. Here EL is acting. Here, yes. Similarly, here EL is acting. Here EL is acting. Yes, compressive EL. What is going to happen? It will try to decrease this length. Yes or no? Yes or no?
Yes, sir.
So what will happen to the, assuming it's a metal wire strain gauge? It's a metal wire. Yes, it's metal wire only. Okay, it's a there are many types like bonded metal wire strain gauges and thin film strain gauges like that. Okay, I'll introduce them tomorrow. Okay, so assuming it's a metal wire. Okay, so I'm going to paste this metal wire by having some, for example, this is having okay, screw kind of thing. I'm going to fix it. A screw kind of thing. I'm going to fix it. Here also I'm going to fix it. That's how I wound this metal wire. What will happen? This metal body is, it is pasted. Okay, either you tie or paste it. Okay, that means paste, bond it on the surface of the load cell which is experiencing or offering strain. What will happen? The strains are acting on this edges. Therefore, what will happen to the net length of this, total length of this wire will decrease or increase? Total length from this point to this point, it will have some so many meters or so many centimeters. This length of the wire, the length will decrease or increase?
Decrease, sir.
Decrease. So what will happen to the resistance? I'm talking about length of, not the block. Okay, length of the metal wire. That's a strain gauge. This is my strain gauge. I'm talking about length of the metal wire. That is the one, the strain gauge. I'm calling it as. Okay, what will happen to the resistance? R will become R minus delta R. Agree? All of you getting? All of you
Yes,
getting?
sir.
And if I mention the gauge factor of the strain gauge, this metal wire strain gauge as SG, straight away I know delta R by R divided by the strain sensed by the strain gauge is equal to its gauge factor. Yes or no? Yes or no?
Yes, sir.
Yes, sir.
Then automatically I can find delta R by R, unit change in resistance, as gauge factor into the strain available in the load cell. I have already the strain calculated. Now my gauge is sensing EL only, not ET. I didn't paste the strain gauge in the ET axis. I pasted my strain gauge in the EL axis. Suppose if you want to paste it on the ET axis, means how I should paste means I have to paste the strain gauge this way. So I have to paste the strain gauge this way. That is going to sense what? That is going to sense what? What it is going to sense? It
ET.
is on the ET axis. All of you getting my point? Yes or no?
Yes, sir.
Yes,
So
sir.
this gauge, strain gauge 2 in the given picture is not the EL gauge. It is a ET gauge. Therefore, it is going to have delta R by R. Delta R by R divided by what? Change in resistance of the second gauge.
Divided by ETs.
Yes, tell me what has to be done. All of you getting? Divided by ET only. Delta R by R divided by ET is equal to the, is equal to
SGs.
SG, the gauge factor. But what what is your ET? So for that, so this metal block will be given with Young's modulus of elasticity, and also the Poisson's ratio of this will be given. Then you know very well what is ET. What is ET? So here what is delta R by R? Delta R by R here is equal to SG into what? Transverse strain only. But what is going to happen here means, since ET is always less than EL, correct? It's EL. So since ET is always less than EL, the gauge which is placed on ET axis will have less change in resistance compared to the gauge which is placed on EL axis. Agree everyone? All of you getting this point?
So
Yes or no?
how, sir?
Because we know ET magnitude is always mu times EL.
Okay, got it, sir.
Got it instantly? Yes. Okay, so therefore gauges sensing transferred strain will have, because strain itself is very small. Again, if you reduce it by the factor Poisson's ratio, because ET is always less comparing to EL, so never place your strain gauge on ET axis because strain is less already. Because already we have very small very small strain only to sense. It is already in the order of micro. Again, if you multiply by that 0.4 or 0.3, the Poisson's ratio of this metal block, and again strain you are sensing is going to become reduced, then change in resistance will become even less. Getting Yashwant?
Yes, sir.
All of you getting this point?
Yes, sir.
Suppose, say we know the strain now. What is the strain available? 62.5 micro strain is available. So that means what we are measuring is a force. To treat this like a force measurement system, so the range is 0 to 100 kilo newtons, which is converted into longitudinal strain of what? 0 to what is the maximum strain? 62.5 micro strain, capital S. Okay, agree? Correct, right? Yes or no?
Yes, sir.
That's a maximum EL. So tell me, what is your ET then? ET is equal to, yes, what is the ET? Magnitude only we should talk about. Modulus of ET, talk about it. It is 0 to what? 0 to, because it should not feel it as, yes. What is that? Assuming the Poisson's ratio is given as 0.4, then what is ET? Modulus of ET is nothing but mu into EL. So this is a maximum. So that's a ET maximum. Tell me, what is the maximum transverse strain? Maximum. 0.4 into 62.5. How much?
$25, sir.
Micro?
Strain.
Yes. Okay. Assuming SG1, strain gauge 1, sensing EL. SG2 connected in the strain ambience to sense what? ET. So it is in the EL axis, SG1 in the EL axis, SG2 in what? ET axis. Now tell me, what will be the delta R of your SG1? So delta R is equal to R into SG into EL, it is sensing. And delta R of this is what? R into SG into what? ET, it is sensing. Agree, all of you? Yes.
Yes, sir.
When EL is what? EL is a negative strain. So delta R will be negative. Okay. And this is what? ET is what? When EL is negative, ET will be positive. Why? It is increasing the width. It is increasing the length. Correct? So ET is positive. This change will be positive. This change will be what? Negative. All of you getting? Because EL is negative, automatically delta R will be negative. ET is positive, automatically delta R will be positive. Agree, all of you? Agree?
Yes, sir.
Okay, now tell me, what is the maximum? Forget about this sign. Okay, we know how to play with this. Yes, then what is delta R? Delta R is equal to, yes, forget about the sign. I'm talking about only the magnitude of delta R. What is that? R? Assume the zero strain resistance of the strain gauge is 100 ohms and gauge factor is equal to 2.0. So this is given for the two strain gauges. All are identical, but one is sensing EL, another one is sensing ET. So R is same, SG is same. So therefore, what is your delta R magnitude? Forget about the sign of EL and forget about the sign of ET. Focus only on the magnitude. R is given as 100 ohm, SG is given as 2, and EL is what? Maximum. What is that? 62.5. So maximum EL will produce maximum delta R is how much? 62.5 into 10 power minus 6 is the change in resistance even for the maximum strain. Understand this. How much change in resistance is going to happen in strain gauge? Calculate. That's maximum, delta R maximum. Yes. Are you getting?
Yes, sir.
In ohms. 0.0125 ohm, that's a change in resistance. Therefore, one can happily say in strain gauges, your delta R by R is very, very smaller than 1. Even if you go with the passive transduction bridge, we don't perceive any nonlinearity. Are you understanding this connection? Yes.
Yes, sir.
What is delta R? Delta R is point. What is delta R by R? Yes, that's the easy way. Delta R by R is what? Strain gauge. Factor into strain. And strain is micro. SG is 2. So it is going to be 2 into 10 power minus 6. Okay, in the order of that only. Okay, right? So delta R by E is so small. So happily you can go with the passive bridge itself. You don't need active transduction bridge when you play with strain gauges as sensing elements. Able to connect now? Because already you know about transduction bridges. Now, because that is going to be the next element, because you know, you understood how you can convert force into stress, stress into strain, strain into what now? Change in resistance using strain gauges. Okay, I'm talking about two sensing element. One is a load cell. There is a one responsible to convert the force into strain, and strain gauge is pasted on the strain surface, which is offered by the load cell, and it is simply sensing the strain, converting that into change in resistance. So one is a primary sensor, that is a load cell, and another one is a secondary sensor, that is our strain gauge. Clear? All of you getting this point? Is he right?
Yes, sir.
Yes, sir.
So now, okay, so it's proved. What is your delta R then? So delta R magnitude will be 0.4 times 0.0125. Straight away I can say, because ET and EL are differing only by what? The Poisson's ratio, 0.4 times it will be. Correct? 1 minute, stay online. Is he right? Is my perception correct? Yes or no?
Yes, sir.
Same, right? 0.4 into 0.0125 only, right?
Yes, sir. Yes.
Yes, sir.
Okay, then what is the number? It's even less if it is ET gauge. That's a point I want to convey here. Okay, so therefore, don't place your gauges on. Yes, don't place your strain gauge on. That's a conclusion. Where the strain is maximum, EL axis or ET axis?
Axis.
EL axis, always longitudinal strain is more comparing to transverse strain. Therefore, place your strain gauge only in the maximum strain axis. That's a rule of thumb. Okay, that's how. Okay, you need to have a knowledge. You have a load cell, you're understanding where the strain is maximum. Place a strain, okay, in the axis where the strain is maximum. So that maximum change in resistance you will get. So what is this number for analytical stuff? What is this number?
0.0051.
0.00?
5 ohms.
5 ohms. Okay, so it is less. So this is much better comparing to this one. Okay, so that's what happens if you suppose a designer may place a gauge intentionally on ET axis. Then by mistake, don't bring EL into the play. You have to see whether the gauge is sensing EL or what? ET. That's why I have shown both the gauges now in this example. So gauge 1 is sensing longitudinal strain. That's a force axis strain. That's a compressive. That's not a problem. I'm not talking about which one is negative, which one is positive. Which one is offering more change in resistance? The change in resistance may be positive or negative. Since it is negative, if you talk about the resistance of this, the net resistance of this is going to become R minus delta R only. When the net resistance of this means, what is that? Net resistance of this will be, let me take it here itself. 1 minute. What is the net resistance of this? If I talk about the net resistance of this, what is the net resistance of the gauge 2? So call it as gauge 1. It's RG1, gauge 1. I'll call it as RG2. What is RG2? Gauge 2 resistance is going to become R plus delta R. Getting? Yes or no? Yes or no? Following, right?
Yes.
Okay, then what is RG1? RG1 is equal to R minus gauge 1 is sensing EL. So it's a delta R due to EL. Okay, so it's a negative strain. And gauge 2 is sensing what? ET. Okay, that is delta R due to ET. So it's R plus delta R due to ET. So we calculated them. Already I have given plus and minus because it is a compressive strain. This is a tensile strain. Already sign is given. Don't bring the sign once again into the play. Delta R due to EL is already known. How much? 0.0125 is delta R due to EL. And this is a delta R due to what? ET. Correct? Getting everyone? Following, right?
Yes, sir.
So the result is going to be RG1 is going to have a resistance what? R. That is what is R now? 100 ohm. 100 minus 0.0125 ohms is the actual gauge resistance. This one RG2 will be 100 plus 0.005 as you said. Correct? All of you getting? Yes or no?
Yes,
Yes,
sir.
sir.
So what's RG1? Calculate that number.
9875, sir.
9875 ohm is the actual resistance of gauge 1. RG2 100.005 ohm will be the RG2. Agree? Love you. So this is your ET gauge. So the change is different. Okay, a different change in resistance. Okay, happening in RG1, RG2. Now the plus and minus is very important. EL is negative strain. It's a compressive, so it is maximum change, but it's a negative. So go with the negative. Compressive strain. EL is compressive, so the compressive EL sensing gauge will have change in resistance as negative. Whereas the ET gauge, it is having a tensile transfer, so the length is increasing. So ET axis parameters increasing, so the resistance will be increasing. Okay, so go with plus. So positive strain, positive change in resistance, negative strain, negative change in resistance. Hope it is easy. Don't put the negative sign to delta R. Okay, keep the delta R sign less, and sign is given only here. If it is positive strain, make it positive. Negative strain, make it negative. Understand? All of you getting? Yes or no?
Yes, sir.
Now you should think of transduction. So now we know how to convert force into strain. Straight away, the load cell plays a role. That's a primary sensing element. And strain into what? Change in resistance. Who plays a role? Strain gauges are playing the role. Correct? Easy? Easy?
Yes, sir.
Then we should convert change in resistance into change in voltage. So familiar route. What is that? Transduction.
Which
Transduction bridges. That's all. So then it is going to become a force or load measurement system. That's what your weighing scale is. Okay. So transduction followed by it is bridge. So V naught of the bridge. Then you can convert that into V naught. What is this? Signal. Signal
Conditioning.
Yes, that's what. Okay. Able to see? The primary sensor load cell, secondary sensor strain gauge, followed by a transduction, followed by a signal conditioning. Finally, you will get the desired output. So 0 to 100 kilonewton can be converted into 0 to 1 volt, like what we did earlier for the temperature measurement. Temperature measurement 0 to 100 degrees C. We made it what? 0 to 1 volt. Same way, you can convert 0 to 100 kilonewtons into 0 to 1 volt. See? Getting now, it's a new measurement system. We can call it as a strain measurement system or force measurement system. So through the load cell, through the strain gauges. Easy? Easy, right?
Yes, sir.
So then I will show a strain environment. Tell me what is the output of the transduction bridge. So this is my load cell. The force is applied here. This is 1 centimeter. This is 4 centimeter. This is also 4 centimeter. Geometry is given. Okay, force is acting on this. The force acting on this is, for example, 200 kilonewtons is given. Then Young's modulus of elasticity for this metal block is 2 into 10 power 12 again, or simply 10 power 12 Newton per meter square I will take, and the Poisson's ratio is given as 0.4 for this metal block. Okay, and I'm going to place one strain gauge here. Okay, that strain gauge is placed. Then I have the bridge now excited by 10-volt supply. It's connected to the ground. Okay, so here I have a resistance of 100 ohms. This is 1 kilo ohm, 1000 ohms. This is also 1000 ohms. Fixed resistors. And here I'm going to connect my strain gauge. Are you getting my point? Yes.
Yes, sir.
Yes, sir.
That's SG1. This is going to offer gauge resistance RG1 between the, in this arm of the bridge, I'm going to connect RG1 considering wire resistances are negligible. This is wire 1 and this is wire 2. Okay, assuming 0 wire resistances and gauge resistances given as RG1 is equal to, yes, R plus or minus delta R, correct? If strain is positive, delta R will be positive. If strain is negative, delta R will be negative. Now I'm asking in the setup, what is the output of the bridge? For some reason, I'm saying this is plus and this is minus. So what is V naught of the bridge in the given circuit? Simple problem. Can you answer? With that, we'll conclude the day. That shows you understood everything. That's how we can expect a good problem. You have a load cell, you have the strain gauge. Yes, you would run whatever the steps we made earlier. You have to make it quickly. Enough data is given. Yes, I have to give only one for the strain gauge. For the strain gauge, assume R is equal to 120 ohms and SG equal to gauge factor is equal to 2.0. Zero strain resistance is given as 120 and gauge factor is given as 2.0 for the strain gauge. Yes. What you will do?
So it's 100 ohms, sir.
120.
Also on the bridge, sir. 100 ohm resistor is there.
Okay, 1 minute. Then it is 120. Okay. Hope it is making sense.
Yes, sir.
Because if there is no force, what is the value of RG1? If force is 0, yes, you Priya, force is 0. What is RG1? R only.
R.
It's 120 ohm. So what is the potential at this point? You can call it as VA. You can call it as what? VB. VB always 5 volts. And V also going to be 5 volt. Bridge will be in.
Balance condition.
Balance
sir.
condition. So when there is no strain, there is no change in resistance, bridge is absolutely in balance. The moment you apply the load, there is a strain, there is an unbalance, there is an output. Then yes, it's making sense. Okay, so no strain, no output, no force. Okay, no output. There is a force, there is a strain, there is an output voltage. Meaningful? Yes.
Yes.
Yes. Now tell me how to proceed. Convert force into
Strain.
stress. Yes, stress or strain. Okay, what is strain? Straight away. Straight away, you remember Young's modulus is equal to stress per strain. Correct? Straight away, go for the strain. Okay, what is your area? Where it is acting? What is the area of surface area? It's 4 cross 4. Yes or no?
Yes, sir.
4 cross 4 centimeter square is your surface area where the force is acting. Yes, then straight away it is force is given 200 kilo newtons divided by area is 4 cross 4, 16 into 10 power minus 4 meter square. Okay, so into E. Okay, that's your Young's modulus. So therefore E is equal to 200 into 10 power 3 newtons divided by 16 into 10 power minus 4 meter square into your Young's modulus. That's your E. What is the E? Capital E. Small e strain, capital E. Okay, Young's modulus of elasticity. What is that? 2 into 10 power 12 Newton per meter square. Are they getting cancelled now? Yes, right? Yes or no?
Yes, sir.
So then result is micro strain. Yes, get the result. So numerator is 2 into 10 power 5 and denominator is, so this 2 and 2 will get cancelled. So simply it is what? 10 power 5. So 1 into 10 power 5 it is. And what else is in denominator? So 16, 10 power minus 4 into 10 power 12. It is going to be 16 into 10 power 8. Agree? Yes or no?
Sir.
Then you get 1 by 16 into 1 by 16 into 10 power minus 3. Yes, get me. What is the number now? In micro, please get the resultant. What is 1000 by 16?
62.5.
Okay, sorry, fortunately, we're getting the same number again. Okay, so, okay, fine, accept it. Okay, there is no other choice. Okay, fine then. Micro strain again. Getting all of you? Use capital S to represent your strain. Capital S, okay, represents strain. Because small s, we feel like microsecond. Okay, so capital S, like Siemens symbol, it's a strain symbol. Okay, getting Ashwant?
Yes, sir.
Yes, E is known. This is a longitudinal strain only. Where the gauge is placed, in EL axis or ET axis?
EL axis, sir.
ETX.
Check.
ET.
ET
EL.
or EL? Yes, that's very important. So this is your force axis. So this is your EL. This is your EL. This is your EL. Yes, sensing what? EL compressive, correct? Yes or no?
Yes, sir.
This is EL. This is EL. This is your ET. This is your ET. Getting Akshaya?
Yes, sir.
So it's EL. So it is reducing the thickness. So this is your thickness. This is your thickness. This is also your thickness. This is also your thickness. Yes, thickness is getting decreased. So it is nothing but your. So you are compressing. So thickness is getting decreased. So it is on the EL axis only. So therefore, RG1 is going to become R minus delta R. It's a compressive negative strain. R minus delta R. That's your RG1. Then you can calculate your VA and then you can comment on VB is always equal to what? 5. So find out delta R and complete the problem. Okay. Yes. Find out delta R. So what is your RG value now? E is known. So then calculate your delta R by R is equal to its EL axis only. So just go for your delta R magnitude SG into EL only. So therefore delta R straight away can say delta R by R is equal to By habit, you will get this equation quickly. So then delta R is equal to R is given 120 ohms into SG is given 2.0 unitless. EL is also unitless 62.5 micro. So 10 power minus 6. That's your change in resistance. How much?
So 0.015, sir.
0.015 ohms. Getting Ashwant?
Yes, I getting.
Therefore, your RG. So I'm putting the negative sign here. I'm not talking about that EL is negative. Okay, so I have a habit of, so here you represent it's a compressive strain, so put minus. Delta R, you find only the magnitude. So based on strain, positive or negative, compressive or tensile, you make the sign. The sign is negative if it is compressive. If the sign is plus, it is nothing but tensile. Tensile take positive, compressive take negative. Okay, Akshaya.
Yes, sir.
Then what is your R? 120 ohms. 120 minus 0.015 ohms will be your resistance of the gauge RG. Yes, what is that number?
So 119.985, sir.
985 ohms.
Ohms.
Okay. Then can you tell me that's your RG? So can you tell me from this what is VA? VA is the potential division between 120 and RG1 excited by 10 volt. Okay. So can I write VA equal to RG1 divided by RG1 plus 120 into 10 volt. Agree? Is he right?
Yes, sir.
VB is 5 volt. Okay, now let us find VA. Following Akshaya.
Yes, sir.
Yes, goal is to find V naught of the bridge. What's VA now? VA is equal to, yes, RG1 is known. How much? 119.985. Getting? So it's 119.985 ohms divided by total 120 plus this. 120 plus this is going to become 239.985 into 10 volt. That's exact number of VA, and VB always remains 5 volts. Okay. Now tell me what is this number accurately. That's what happens in the transduction bridge.
So 4.999687.
999.
Yes, sir.
Okay. Yes. Then
68748, sir.
6. Okay. See this. Okay. So let it be. Keep the number as it is. And VB is 5 volt. So then V naught of the bridge. Now you understand why I put VA negative. Who is higher potential? VB or VA?
VB, sir.
Okay, understood now. Sometime problem is I will call this as B point. I will call this as A point. Simply will be asked to mark the polarity marking of A and B. So now after knowing the potential only, you can say what is higher potential, what is lower potential. It's clear now why that polarity marking is given. Actually, clear now?
Yes, sir.
Then V naught of the bridge is nothing but VB minus VA. Yes, subtract this from 5 and put the resultant in milli or micro. So put the output of the bridge in milli or micro.
Sir, it's 312.52 microvolts, sir.
312
52, sir.
1 minute. Stay online. 1 minute. Are you seeing the full screen?
No, sir.
Whether the slide is displaying on the screen?
Yes, sir.
Okay, 1 minute. Okay then. Yes, what is the number now? You can say, your Priya. 0
Sir,
point.
sir, 312.52 microvolts, sir.
Is it okay?
Yes, sir.
Yes. So you have to check whether the answer is in milli or micro. Usually the transduction bridge, even for such a huge strain, that's a problem. You're giving 200 kilonewtons, the bridge output is just even few millivolts only. That signal is very vital in strain measurement, because the strain we are going to get from the load cell is going to be in the order of micro only. So bridge is not going to produce a strong potential. So that demands lot of signal conditioning work. So much amplification needed during signal conditioning. By default, it is achieved by instrumentation amplifiers only, because they are capable of having the gain up to 2000. Correct? So since the output of the transduction bridge is always going to be in the order of millivolts, because change in resistance is very, very small, because the strain is only in the order of what? Micro. So micro strain is converted into millivolt only. So we have a huge challenge of making the output in the order of volt. So we need to convert milli into volt. Roughly what's the gain needed? 1000, more than 1000.
Yes, sir.
By default, we need to go with instrumentation amplifier as your signal conditioner. And moreover, it is producing what? 2 output terminals. So happily you can connect this to what? An instrumentation amplifier only as a signal conditioner. Then you can set the gain suitably. Okay, so that you can convert that into 0 to 1 volt. Now I have shown you a complete setup of strain measurement. Only the signal conditioning part alone is not given. So you know how to do the signal conditioning for this. Clear? Clear?
Yes,
Yes, sir.
Okay, yes, that's a complete setup for force measurement. Understood the load cell, how it is converting the force into strain. A lot of mechanical parameters we played, we established good connection, and finally we play with the strain sensor. Okay, but instead of doing all these things, and your Priya will remember one equation. So can I go by that equation, your Priya? What is V naught of the bridge? It is, you remember, it is single sensing element. Only one element is changing its resistance. Then you remember the equation. It's after all E by 4 into delta R by R. It will still work. Okay, for this. What is E? Excitation of the bridge. Don't get conflict. This E is not the Young's modulus. This E is the excitation to the bridge. How much?
10 volts, sir.
Divided by 4 into delta R by R. Delta R by R is nothing but gauge factor into the strain. You don't need to calculate delta R also. Straight away delta R by R, because we know that fundamental gauge factors delta R by R divided by strain is equal to the gauge factor. Exploit it always. So you don't need to calculate your delta R, waste unnecessarily the time. So V naught of the bridge is going to be for the given polarity marking. It is correct. Either it is going to be plus or minus. That's all. If VA is positive, V naught of the bridge will become negative, but the magnitude of the bridge output will be always this. Okay, so if you properly put polarity marking for A and B, this is always positive. So then 10 by 4 is nothing but 2.5. So 2.5 volts into, what is Hg into E? Hg is 2.0. What is E? 62.5 into 10 power minus 6. Now tell me what is the result in milli? 2.5 into 2 is 5. 5 into 62.5.
0.3125, sir.
Exactly same number.
Yes, sir.
And prove this. Okay, yes, prove this. So prove this how the bridge is. So this is called a quarter bridge. This is called quarter bridge. Okay, so quarter bridge means the bridge function of only one sensing element. How many fixed resistors? 3 fixed resistors, correct? Only one is variable. Usually, I need not to go with this 1000. I can also give this as 120. I can also give this as 120, but that's not a problem. What resistor here using is not a problem, because that is going to keep only VB equal to what? 5. But as a habit, I will mark this as R, I'll mark this as R, I'll mark this as R, and this will be R plus R minus delta R. Agree, all of you? All of you getting? Yes or no?
Yes, sir.
Yes, sir.
And this is your E. So I'm giving you this bridge. Tell me what is V naught of the bridge. You prove this. So this is R. So all are having R only. Okay. So this is R. So you have to prove it. So try this and show me this result tomorrow. Okay. E. And this is the ground. Okay. So I'm taking this is a fixed resistor. This is a fixed resistor. And this is a fixed resistor, and this is R plus delta R. I am saying, for example, then this is the voltage. I'm calling it as VA, and this is the voltage. I'm calling it as what? VB. Now tell me what is the difference the bridge is producing V naught of the bridge. Okay, this is VB. So you know very well who is higher potential now? Who is higher potential now? VA or VB?
VB.
Yes, check once. Who is higher potential?
VA, sir. VA.
Yes, this is the potential. What is that? VB. It's a voltage across R. VA is voltage across this. So it is having more resistance. So it has to be higher potential. This VA, right? So then this is higher, this is lower. So this is producing A by 4 into delta R by R. Show this. You may need an assumption delta R by R very, very less than 1. It is so. It is there. So happily one can say this. Getting you, Priya?
Yes, sir.
So this is one practice problem you can try. And I'll give one more practice problem. You can also try this. That's a second example. So what is the time now? Anyone?
9:30, sir.
Okay, I'll complete now. So this is E. Okay, this is R. This is R. This is a sensing element, but sensing compressive, and this is sensing tensile. One is R plus delta R, another one is R minus delta R. Find out this output as well. So two sensing element, we call this as a off bridge. Two sensing element, half of the bridge is filled by sensing elements. Getting the logic? Getting the logic? Yes or no?
Yes, sir.
Then who is higher potential now? This is still the higher potential. This is the lower potential. That's a V naught of the bridge. I can mark it here itself, but for clarity's sake, I'm taking this way. This bridge is off bridge. You can think of full bridge, a bridge full of sensing elements. Okay, full of strain gauges. Okay, so this is called quarter bridge. So only one element is. So quarter bridge makes your output quarter of E into delta R by R. Is it okay? Quarter of E into delta R by R. Easy, right?
Yes, sir.
If it is off bridge, half of E into delta R by R. Agree? Prove it. Getting everyone? Yes?
Yes, sir.
If it is a full bridge,
E into delta R by R.
E into delta R by R. That's what going to happen. But you have to connect your elements carefully. So suppose if I connect this way, 1 minute. If I connect this way, you try what is the output it is producing. I'm connecting R minus delta R here. I'm connecting R plus delta R here. This is R. This is R. Excited by E. It is connected to the ground. Find this output. That's also an example problem for you. Yes, find this output. That's a V naught of the bridge. Find this. Can I say it is still same? Not sure, right? Okay, here also you must be not sure. Okay, so prove this. Okay, so that's example 2. This is example 1. Okay, you're going to try this. Okay, so tomorrow give me the solution. Example 1, example 2, and example 3. Example 3, I'm not saying what is the output. Example 1 and 2 are proving example. So prove this is V naught of the bridge. for the quarter bridge and prove this is V naught of the bridge for the half bridge. Fine, Priya.
Yes, sir.
And can anyone say what will be the output? A quick guess? Ishwant?
Sir, I've seen this somewhere, but I don't remember now, sir.
Okay, prove the output is 0. Prove the output is getting. Able to follow me?
Yes, sir. Yes.
But you'll get surprised, but it is not in balance. Yes or no? Product of opposite resistors are not equal. Then how the bridge is in balance? How the output is 0? You do that example 3, then check whether V naught is 0 or not. Okay? Okay?
Yes, sir.
Yes. Okay. Yes, 3 examples you can try. Okay. So tomorrow means we'll meet on Monday. Okay.
Yes, sir.
Any other doubts you have to discuss? Yes, Akshaya.
Sir, no, sir.
Fine then. So shall we conclude?
Yes.
Okay, then it's time for dinner. So we'll meet soon. Okay. So yes, go through this sessions once again. Okay, if necessary. If any doubts, yes. Okay, WhatsApp. We'll discuss in the next class. Fine, everyone.
Yes, sir.
Yes, thank you. Good night.
Thank you.
Thank you, sir.
Thank you, sir.